Hello, good evening. Today I'm going to be responding to some of the questions that I've seen through this chat, specifically some of the questions regarding polynomials. So, as all of us you might know, the polynomials are a very intrinsic part of algebra, and knowing how to manipulate them and how to extract information from them based on rules and theorems and other parts of the mathematical sciences, it's very important moving forwards afterwards. So today I will be going to explain three different problems. The first one is going to be dealing with how to calculate the zeros of a polynomial. The other one about inequalities, and finally how to process synthetic division. Okay, so for the first one, we want to find, let's see, p of x is equal to x cubed plus 4x multiplied by x plus 4. Okay, so the first thing to understand in here, to find all the zeros, we need to convert this into an equality equaling, of course, to 0. An advantage of this polynomial is that it's already in our, it is in a factored form. So finding the zeros shouldn't be that hard. And if you remember from the fundamental theorem of algebra, it tells us that the degree of a polynomial is the number of roots that the polynomial has. So how do we find the degree of the polynomial? It's going to be the multiplication of all of this x's, well, expanding this polynomial and afterwards seeing how much do we actually obtain from this. I'm not going to do that just right now. I'm just going to continue manipulating this polynomial and equaling all of this to 0, and we're going to see why is it that the fundamental theorem of algebra tells us, yeah, you might you're going to find the roots, but some of these roots are not necessarily going to become x-intercepts because, well, as you have perhaps an idea, we have imaginary and real numbers. Okay, so moving forward, I'm just going to this red part, going to make it a little bit um, more factorized. So this can be rewritten as x times x squared plus 4 and x plus 4 in here. I'm not moving anything of this, so this is going to be equal to 0. By making this equal to 0 and knowing that it's x is multiplying this other polynomial to the right, this means that we can make everything equal to 0 from here. So the first polynomial is going to be x equals 0, right? Which is this first one. Let me just put a little tag in here. So this is the, oh, sorry. This is the first one. Right? The second one is this, and the third one is this. So the first one is x equal to 0. We have already found a root for that one. For the second one, we have x squared plus 4 equal to 0. For this second one, if we want to solve for x, we would do x squared equals to minus 4. And we would apply the square root to both sides, right? So square root or elevating both sides to 1/2. That means that we're going to have the square root of x squared is equal to the square root of minus 4. And we know that, well, the square root of x squared is going to be x, and the square root of minus 4 is going to be a negative number inside the square root, which is not valid. We can rewrite this one actually as the square root of, oh, I'm going to make it larger, square root of minus 1 multiplied by 4, right? We do know the square root of 4, which is equal to 2. And this is the square root of minus 1. And the square root of minus 1 can be rewritten as 2i. So I don't know if you're familiar with this concept. I think you are. And we have to understand that the square root of I is just, sorry, that I is equal to the square root of minus 1. It's just a representation, a mathematical representation of what an imaginary number is. So let us not forget that since we have squared everything up, that means that the results that we're going to get here from this root is x equals plus minus the 2 times I. Okay, so we have two different roots in this solution, right? So first one we have x equals 0, and the other one we have two other roots, x equals plus minus 2i. And the third one is pretty much the same as before, x plus 4 equals 0. So this leaves x equals 2 minus 4. So finally we have 1, 2, 3, 4. 4 different roots, but out of them, we can only account for the x-intercept of the polynomial to be x equals 0. So for the first one, for the first term, and for the third term, x equals minus 4. So the x-intercepts, I'm just going to write it like this, are x equals 4 and x equals minus 4. Because the other ones are on the complex plane and we cannot count them in. Okay, so that is the first one. Let's go to the second problem. Let's see. We need to solve an inequality. This inequality is x cubed plus 4x multiplied by x plus 4 less or equal to 0. Okay, so this inequality, to solve inequalities, is pretty much the same steps as before, except that in an inequality, what you're going to have for your solutions are a range of numbers. And this range of numbers is going to come from how you have solved your factor of your system. So the first thing that we need to do is we can momentarily, of course, forget about this less or equal symbol in here, and we just continue working with the solution that we have, the polynomial that we have. And we can expand this polynomial actually to make it a little bit more readable. Actually, yeah, I think, yeah, we can expand this, making it like x squared plus 4, right? And x plus 4 equals 0, right? And this would mean that we have same as before, actually. Yeah. X equals 0, right? So that is one of the solutions when it's equal to 0. X equal to plus minus 2i, because it's exactly the same as we did before, and x equals to minus 4. Now, what we need to do is to check the critical terms. So what are critical points? Critical terms are the ones that are, well, intercepts, right? And that are on the real plane. So we have to forget about this values right here. I'm gonna drop this to, and you're just gonna focus on 0 and minus 4. So first thing that we have to do is to check if the intervals are in between the critical points, right? So we need to test values for um, values that are either before the smallest values of our roots or above our largest values. So if we try with a number that is less or equal than -4, say with -5, so with let's try with x equals -5. If we plug in x equals to -5 in our original inequality, I'm going to have a 5 times 5 squared plus 4 times 5 plus 4. And how much is that? Let me just really quickly grab my calculator here. It means is 5 times 5 plus 4, right? This is times 5 plus 4 times 5. And since it's not less or equal than 0, that means that this value is not working for us. So anything below this interval has to be dropped out. That is why it's important to understand that this value right here is our lower limit for the solution. Now let's try for any value that is in between x less or equal than -4 and x equals to 0, right? So whatever is x less or equal to -4 and 0. So let's try with, I don't know, -2. Okay, so -2 times -2 squared plus 4 times -2 plus 4. So I'm not going to use calculator. Let's see, it's -2, 4 plus 4. This is this is 2. So we have 4 plus 4 is 8. -2 times 8 times 2 is going to be -32. And that is less than 0. So that means that this value is checked. And finally, for any value that is larger than x, let's put it like this, that x larger than 0. So see how I'm not including 0 in here because originally the inequality stated that 0 was also included in the solution, in the solution. So I'm just going to leave it like this and try it out with let's say x equals 1. So for x equals 1, I'm going to have 1 times 1 squared plus 4 times 1 plus 4. That means that whatever multiplication I'm going to have in here is going to be positive, and it's not going to work on our original inequality. So the solution, the interval, the range of solutions for our inequality must be in between x equals -4 inclusive and x equals 0 inclusive as well. Okay. So finally, I think we have the largest polynomial in here. Yeah. We're going to be working with the remainder theorem and synthetic division. And we're told that we have a polynomial p of x equals 2x cubed minus x squared plus 3x plus 2. Right. Let's see. Okay. So the first thing that we have to do, I'm just gonna check if it's working properly. Yeah. Okay. First thing that we have to do is for the remainder theorem, it tells us that we need to do a division between, well, right now for value x equals 1/2, and what it tells us is that we need to do the synthetic division between this polynomial and the polynomial x minus 1/2. So extending this, it actually represents x equals x minus a. So you can have whatever value of a, and what you want to do is um, find based on the theorem what are um, the remainders. And the solution of the theorem says that if we divide this x minus a over the original polynomial, the remainder is going to be equal to p of a. Okay, so let's go ahead and do that. Synthetic division. What we require for synthetic division is going to put it like, yeah, I'm just going to put the large polynomial in here. No, I'm not going to put that. Just going directly into it. So I'm going to put a 1/2 in here, a divisor like this. So that it's understandable like this, and then it comes in here. And so a little bit here. Yeah, and then we need to put in here the value of a, right? And afterwards the um, coefficients that are directly posed to the variables of our polynomial. So in here 2x cubed, we're going to put a 2, and then we go into, if for instance this x squared wouldn't exist, we'll put 0. But right now, since it exists, we'll put -5. Then same idea, right? If the x wouldn't exist in here, we'll put 0, but since it exists, we'll put 3. And then the final value in here, which is 2. So we need to put this value, the first value goes down. Afterwards, we multiply. 1/2 times 2 is equal to 1, right? And then we make the summation of the first coefficient time over the this multiplication that we just did. So it's -5 plus 1 is equal to -4. Now, we repeat this process until we go into the last value, and that is going to be our remainder. So 1/2 multiplied by -4 is equal to -2, and then 3 minus 2 is equal to 1. 1/2 multiplied by 1 is equal to 1/2, and 2 plus 1/2 is equal to 1/2. Okay, so let's remember that we can put this as, let's see, 5/2. 5/2, right? And again, going back into the remainder theorem, says that the remainder of this division is going to be equal to P of A. So P of A P of 1/2 is going to be equal to 5/2. We can verify this by putting 1/2 here, and afterwards you're going to get the same result. If you have any more questions, if you have any other suggestions to the solution, please let me know. I'll be very happy to help you out. I'll be around here for the next hour and a half. So just feel free to contact. Right. Goodbye.